Our project was to revamp a 30-year-old vending machine to utilize coins, bills, and magnetic strip cards. This vending machine would also be networked to utilize an online server to track transaction history and inventory of the machine. IEEE can use this machine to stock with commonly used parts for labs that students could purchase in the middle of the night when the IEEE store is no longer open. Students will be able to use their student IDs for purchases. They can put credit on their card either via the IEEE store or going to an online website and using a credit card to place credit on their student ID. This will allow students that don't carry cash to still get parts out of the vending machine while not having the IEEE pay for the use of credit cards. Using student IDs will also eliminate the need for encrypting credit card data over wireless or wired networks. This will allow the IEEE to use the external server without any type of encryption that would cost money. And finally, the IEEE will eventually utilize the convenience card system in the library to make purchases.
We now move on to our top-level block diagram, which shows the relationships between all the individual component blocks in the top-level design. We begin with a brief description of our serial protocols, SPI, I2C, and UART.
We utilize SPI to talk to our LCD. SPI uses 4 logic lanes to transfer data and can both transfer and receive data simultaneously. By checking a status register, we know when these processes are complete and can then utilize the data to perform specific functions within our blocks. Our second serial protocol is a 2-wire interface known as Inter-Integrated Circuit, or I2C. I2C consists of a serial data line and a serial clock line and works by using a master-slave relationship to send discrete packets of information bookended by start-stop bits. We will be running ours at 3.3 volts and using a 10-bit address space with a clock speed of 400 kilobits per second.
UART is used to interface the card reader to the server to the microcontroller, and the microcontroller to the CoinMech. A baud rate of 9600 is used between the card reader and the server and the microcontroller, and a baud rate of 600 is used between the microcontroller and the CoinMech.
The temperature sensor detects the ambient air temperature inside the vending machine and outputs a corresponding voltage between 2.5 and 5.5 volts to the microcontroller.
The temperature control receives input from the microcontroller and turns on a cooling fan if the temperature is determined to be greater than 115 degrees Fahrenheit.
The LCD receives serial data from the microcontroller and displays product pricing and various greetings to the customer. This is done using a 2-line 16-character display screen, which will be mounted on the front of the vending machine.
The card reader reads the magnetic strip card. Its inputs are 12 volts from the power regulator and the physical card input from the user. Its output is the card reader serial data in UART.
The microcontroller is used to control every peripheral device in our design. It utilizes SPI to talk to the LCD, utilizes UART to talk to the server and the CoinMech, it utilizes USB to talk to the programming computer, and then several logic pins to control the vending machine and the bill mech. It also utilizes I2C to talk to a temperature sensor.
The power regulator begins with a bridge rectifier circuit that transforms the 24-volt AC signal from the wall outlet into a 36-volt DC source that is in turn used to power our temperature control circuit. The signal is then routed through a linear power regulator which sets it to 12-volt 400 milliamps and is used to run our AVR board and microcontroller.
The microcontroller contains a bulk of our code, which is done in C. Each peripheral device has a separate set of firmware which is used to interface the microcontroller to that peripheral device. MySQL is used to form the database on the server. Perl is used as a front-end interface to this database. Perl is utilized to interface the database both to the card reader and to the microcontroller.
This design presented several unique considerations. Not the least among them was the fact that the vending machine, being a nearly 50-year-old proprietary design, possessed nearly no documentation. This meant that the internal functions of the machine had to be reverse engineered before any attempt could be made to physically interface our design with the old machine. This was additionally complicated when the machine's main board was inadvertently destroyed during testing, leaving only the original analog price board. As such, we were now forced to integrate not only our design, but also the coin and bill reader. At this point, the scope creep became exponential. Instead of finding an access point on a digital board, we were forced to re-engineer an AC to DC interface between our modification and the vending machine. With this in mind, we decided to make our AVR board the new central control of the machine, routing all commands through it, while at the same time placing most of the newer card functions off-site on the network server. The result, while far from what we had originally intended, allowed us to fulfill the project's specifications.
This is an overview of our vending machine modifications.
From the vending machine, we have a 24-volt RMS coming to a power regulator circuit which rectifies the voltage to 36 volts VDC with an appropriate ripple of 0.06 volts. This is done using a bridge rectifier. This voltage is then made available to the temperature control circuit as an unregulated voltage rail VDD, whereas two more voltage rails VCC, each at 24 volts VDC, are regulated from the 36 volt source as 1 amp voltage rails used by the microcontroller.
The temperature control circuit uses our 36 volt DC line, the VDD rail, to power a 12 volt fan turned on by an NPN transistor which is controlled by one of our AVR board's 5 volt lines. The airflow produced by the fan is intended as an overheat protection in case the power regulator circuit grows too warm.
In order for the temperature control circuit to sense an overheat, our design includes a temperature sensor that uses I2C to communicate with the microcontroller. This sensor requires 3.3 volt power, which we supply with a separate regulator, and it communicates to the microcontroller using a data and clock line.
The AVR board is the central nervous system of our project, with our microcontroller acting as the brain. It receives input from and interprets the signals of the coin machine, card reader, and keypad, as well as managing the server data and vending cycles. It uses these to control the temperature control circuit's fan and the screen outputs of the LCD.
From the microcontroller goes the connections needed for the LCD, which is used to display card reader commands and notifications. The card reader, used to relay student ID card data from a student's card to the microcontroller and then to a server, communicates with the microcontroller using serial data over an RS-232 cable. This cable also provides the 4 to 15 volt power to the card reader from the microcontroller RS-232 port. The microcontroller takes a signal from the coin mech and determines, when the button is pressed, whether or not the price matches the price board, and if so, the microcontroller activates a relay which supplies power to the vending motors. This same process is replicated with the card reader, but with the card balance available on the user's ID card. And here's what you've all been waiting for: a demo of the card reader, ID validated, item vended, and of the coin mech. In action.
Here are a few suggestions from the members of Group 17 for all future senior design students.
Get an early start.
Be open to suggestions.
Never be afraid to ask for help.
Check your ego at the door.
Be flexible.
You will get annoyed. Learn to deal with each other.
The internet is your friend.
Expect long hours.
Always, always, always turn off the power before moving the probe. So that's our project. We've given you an overview, taken you through our block diagram, described our very unique design considerations, and finally given you a full inside look and demonstration of exactly what goes on inside our project. So for Ryan Nelson and Stephen Roderick, I'm Paul Lyon, and we are Group 17. Thank you for watching.